Swayam Prabha. Digital India. Educated India.
Okay, so in the previous lecture, we looked at the various conformations that we'd be interested in developing a model with, and these conformations are the ones which have the groups which are perpendicular to the carbonyl, and so we drew them out. There are 6 of these conformations. So here is the phenyl ring which is perpendicular to the carbonyl, and there are various other sort of similar conformations, and from this we sort of deduced that the 2 important ones are the ones where the largest group is furthest from the carbonyl. So it's important to note in this model that just to understand this whole framework under which we are operating, there are several models which account for the selectivity that we observed. So if you remember, we are trying to develop a model that helps us rationalize the 3-to-1 selectivity that we get in the nucleophilic addition reaction. And so one of the models is this. Okay, so this model sort of tells us that you need to place the largest group, perpendicular to the carbonyl. Okay, so as a general model, what we need to look at is we drew out these 2 structures here. So that is, one is this, where you have the C double bond over here, the hydrogen here, the phenyl ring was over here, methyl was here, and H was here. Okay, and the other conformation was the following, where you had C double bond O. I think by this time you are getting quite familiar with drawing out these various conformations. And so according to the model that we are trying to develop here, the important conformations are these. Okay, and wherein the largest group is perpendicular to the carbonyl. Okay, and now what we need to sort of figure out is, we already know that the attack of the nucleophile on the carbonyl, so this is your C double bond O, it does not occur at 90 degrees. So that we already know. And so the attack actually happens at 105 to 107 degrees. So depending on which source you follow, this is called the Bouguereau-Dennett's angle, and it ranges from 105 to 107. Okay, so this is kind of the angle at which your attack is going to happen, right? Now, let me just draw this out. So this is the Bouguereau-Dennett's angle, which is 105 to 107 degrees. If you look at Claydon, the book refers to it as 107 degrees. I'm sorry, this is the whole thing. And if you look at the other sources, it says about 105 degrees. So this is the sort of range that we're looking at. Okay, so this is the angle of attack. So we know all of this because we have developed the framework based on the main parameters that help us understand this angle of attack. Okay, so now how do we account for the difference in reactivity? So the difference in reactivity can now be attributed to the one which has the least hindered approach. Okay, so I will repeat. So the attack that has the least hindered approach is the most favorable or the least energetic. Okay, so just to put this in perspective, let's look at the reaction profile. Let's say A goes to B, right? Now if you want to look at something like, here is the transition state. Okay, so energy, reaction coordinate. So let's say I go now and make another analog, A1, okay, or A2, and if anything that results in an increase in the transition state energy. Okay, so let's say I'm going through this pathway to give me B1. Okay, now this difference in energy is going to destabilize the transition state, in which case the rate is going to be going down. Okay, so anything that destabilizes the transition state is going to result in reduction of rate. Anything that stabilizes the transition state or removes the hindrance to the reactive center is going to result in a decrease in the transition state energy, which results in an increase in rate. So now coming back to the picture, I'm just taking this out from Claydon so that you guys can go back and refer to it. So therefore, these are the major paths that we are looking at in which the nucleophile can attack. And now among these 4 paths, what we can sort of try and understand is that there are 4, this nucleophile can attack from here, this conformation it can attack from here, it can attack from here. Okay, so in these ones that are highlighted yellow versus the one that is highlighted in green, there are differences. So here in this, let's start from the right. So here in this path, for example, the methyl group is quite close, and therefore this path may be slightly hindered, or you can assume that it is going to be hindered. Similarly, here you have a very large phenyl group on this position, and so the attack at 107 degrees is going to be disfavored. So in this particular conformation, both the attack paths or trajectories are going to be hindered. Whereas in this, you have a situation where the phenyl ring is close to the nucleophile attack, just like the other case, but you have a situation where you can have an unhindered approach. Okay, so the unhindered approach is because of the presence of the hydrogen here over in the other case, the methyl. So therefore, among the various trajectories that are possible, you have a situation in these 4 compounds, in these 4 conformations, you have a situation where a particular path is most favored, and which is this. Okay, so let's try and understand this model a little better now. So you have the nucleophile attacking here from the unhindered side, as we described in the previous lecture, right? Now, what are the products that are going to be formed? So this is going to be an exercise that we need to understand or to pay attention very closely. So if you draw out this conformation, the most important conformation, then you have the phenyl here, hydrogen here, and methyl here, and the nucleophile is actually attacking from here, right, as we described it. And so if you push the arrows, then you get the following compound, which is here, shown here. We have the same ring in the back, so keep the back carbon the same, right, and don't make any changes to this. And now, in order to draw the front carbon, we need to look at it in a slightly more careful way, right? So what happens in this process is that this carbonyl bond is going to break, and this carbonyl bond was sp2 hybrid, and now it's going to become sp3. And so since the nucleophile is attacking from this direction, the C double bond is going to move here. Okay, so you're going to have, just to simplify things, I'm just going to draw it like this. The nucleophile is attacking from here, so the nucleophile is here, the OH is going to be here, and the hydrogen is going to be over here. Okay, so this sort of pushes the 2 groups, that is the C double bond O and the CH, it's going to be pushed in this direction. The carbon is going to assume a sp3 hybridization. Okay, now this is the general model that we're going to follow, and this is the model that we're going to use to understand the outcome. Okay, but now in order to generalize this, the way forward is that when you have a carbonyl compound such as this C double bond OR with 3 different groups. Let's say you have a small group, a medium group, and a large group. That is large, small, medium. Now the strategy moving forward is to look through this C double bond O R group and draw this out in the following way, which is the Roman projection, C double bond O, okay, R, right? And exactly the way you draw it, the large group is always going to be on top. And now if I'm looking at it from here, the small group is going to be on the right and the medium group is going to be on my left. Okay, so this is how I would draw this. Okay, but this is not the important conformation. In order for us to understand the model better, we need to be able to draw it out into special conformations. That is, the first one is this C double bond O R, where the large group is perpendicular. And now you need to rotate the previous conformation that I had drawn and draw out the correct ones. Okay, so this takes a little bit of practice. So I would urge all of you to go back and try out some of these methods for rotation and so on, so that you get familiar with this. Okay, so you have these 2 conformations. Okay, and these are the 2 conformations that are going to be important. And now the question is, which of these 2 is actually going to be more reactive? Okay, so I just want to remind you once again, we are not looking at populations of conformations. We are looking at which conformation is more reactive. And according to this model, the more reactive one is going to be giving you the major product. Okay, so now we know the Bugid and its angle, and so the nucleophile is going to approach from here or from here and so on. So all of this is already known to us. So I'm just recapping this. Okay, so as a general model, this is the one that is used to understand nucleophilic addition reactions on carbonyl compounds. So this model is called the Felkin-Hahn model. Okay, so this is the most reasonable and well studied model which helps us understand additions to carbonyl compounds. And so therefore, and also it has a, it's been figured out using a lot of experimental data. And so therefore this model is the one that we would recommend that you follow to predict the major product. Okay, now going back to the example that we started with, where we found that we were getting one particular major product, the conformations, I'm going to draw it over here, which is C double bond O, ET, okay, phenyl, H, Me. Okay, so this is one of the conformations. I would urge you to go back and work this out. And this is the second one, C double bond O, ET, phenyl over here, and you have hydrogen and methyl. And so keep in mind that these are actually in equilibrium with one another. And given these 2 conformations, we now need to understand what is the most favorable attack trajectory. Okay, so the way we would project forward is that clearly this attack is not very favored because of the methyl group. This one is not going to be favored because of the phenyl ring. The same situation over here, and therefore the most favored one is the one which I am drawing in blue. Okay, so now if we consider that lithium aluminum hydride attacks from this particular trajectory, and now the product that you will get, which I'm just going to draw it as hydride, that is the way we write it is H3AlH minus, and so this is the one that's going to attack from here. So the product that we will get is, start with this, C double bond O, ET is here, phenyl is here, methyl is here, hydrogen is here. And so now, as we discussed, the hydrate is going to attack from here. And so once this attack happens, immediate product that you're going to get is this. Keep the back carbon the same. And now we need to correctly write out the front carbon. So this is OH, H, and ET. Okay. So this kind of a conformation has to be drawn in the correct sort of projection. Let's look at it a little bit closely. So you have OH, ET, and H. Okay. And the three substituents in the back remain the same. So you have methyl and hydrogen. And so the way we would redraw this is in the following manner. Okay, so the way we would redraw this is that we would keep the phenyl ring in the back. Okay, and so now if the phenyl ring is in the back, then the methyl is coming towards me and the hydrogen is going into the plane of the board. And then you have the hydroxyl group is going to be over here, and the ethyl group is going to be in the back. Okay, so this is the conformation or the product that we would expect. Okay, and now if you go back and check the the major and minor products from the previous lecture, you will find that this was the major product that was formed. Okay, so therefore the Falkenhayn model is a very powerful model to help us understand the experimental outcome, and this model has been developed using very rational methods, which is we start with giving out that the largest group is perpendicular to the carbonyl, which is a reasonable thing to propose because the eclipsing interactions are going to be minimal in that conformation. Then we go to and invoke the Bouguer-Dunnett triangle, which was again experimentally derived, and then we also use high-level computational calculations to support the model. And therefore, the Falkenhayn model is perhaps the very reasonable and rational and consistent model that helps us understand the outcome of these kinds of attacks. Okay, so let's just now quickly recap. So when we want to explain the formation of a product, in this case in the ratio of 3 to 1, so we want to develop a model, and the model that we want to use, we prefer to use is the one which is the Falkenhayn model. Okay, and the Falkenhayn model basically has very important characteristics. So that is the large group is actually going to be perpendicular to the carbonyl, and when you draw out this kind of conformation, you will find that there are two conformations and there are four possible modes of attack, and among these the unhindered approach, which is shown here, is the most favored, and that's going to give you the corresponding product. And we also looked at how to draw this product, and this allows us to sort of redraw it and you get this final product. Okay, now as I mentioned here, this is called the Falkenhayn model. Okay, now there are other models which are developed based on completely based on the observation. That is, you get this ratio of major to minor, and you can develop a model which doesn't have a clear logic to it, but still accounts for the formation of the product. And one of those models is actually called the Cram rule or the Cram model. Now the Cram rule is very interesting because it's one of the earliest developed rule in this field, and it's a very powerful rule and it works very well. But the problem with any such rule is that there's no rational basis for us to consider this. Okay, and so the Cram's rule has actually fallen out of favor among scientists, and therefore don't need to discuss it. Okay, So Claydon says, explanations and clear logical thinking are more important than rules, and you must be able to account for and predict the reaction of chiral aldehydes and ketones using the Felkenan model. So we would prefer to use the Felkenan model, and there's a little bit of confusion I see in the conversion of this product to the corresponding structure drawn as shown on the right. So if you have any confusion, the best way to sort this out is actually, since there is going to be an enantiomer that is going to be formed, you can actually assign the absolute stereochemistry. So what I have done is I have just tried to assign the stereochemistry of this carbon over here, and here the OH gets priority number 1, the carbon in the back actually gets priority number 2, ethyl gets priority number 3, and of course hydrogen is priority number 4. And so if I look at it from here, okay, from this side, now it's actually going to go in the clockwise direction, and therefore I have this assigned as R. Okay, now when I'm drawing the next structure, whatever method you follow to draw it, the absolute stereochemistry will remain intact. And so I go back and assign the stereochemistry for this product here, and this is priority number 1, and this carbon here is priority number 2, and the ethyl group is priority number 3, and of course hydrogen is priority number 4. And now when I look at it, actually with the hydrogen pointing towards me, it is clockwise, and therefore it is R again. And lastly, we'll do the assignment of stereochemistry for this final structure over here. This is again taken from Claydon. And so here again OH, this carbon over here, and ethyl, this is 1, 2, 3. And so this is anti-clockwise, but since the hydrogen is pointing towards us, this becomes R. Okay, so when you're in doubt about what the structure that is formed, it is best that you assign the stereochemistry and make sure that the stereochemistry is consistent. Okay, now with this, let's move on to one more example, which is the addition of a Grignard reagent. We'll look at Grignard reagent later in the course, but all of you must be familiar that this is a carbon-based nucleophile. And so when I look at this structure, at the carbonyl, what I want to do is, as we looked at in the in the example, I just place myself over here and look from here. So the carbonyl is on top and the hydrogen is below. And now if the way I've drawn it, the phenyl ring is actually eclipsing the carbonyl, hydrogen is on the right and methyl is on the left. So then what I do is I move on and draw out two different conformations, wherein the largest group is actually perpendicular to this. So I'm just going to draw this in this following manner. I think you guys need some practice, so you should go back and draw these for yourselves. And what you will find is that these are the two major conformations. And when you look at these two conformations, we have attack, which is favored as shown in this orange arrow, which is going to come here. Okay, now the attack of the nucleophile as shown here. So nucleophile here is actually ET minus, and I'm putting this in parentheses because it's not really ET minus, it's ET MGBR. But nevertheless, if ET minus attacks from here, then this carbon oxygen bond is going to break, and you can push electrons here and give O minus, which is going to pick up a proton, from somewhere and pick up this and become OH. So this is going to be the structure of the compound that is formed. Okay. Again, this is all worked out in Claydon, so you can go back and look at it. But just so that we follow the correct convention that I discussed, let us now assign the stereochemistry. So for this carbon over here, the priority number 1 is OH, priority number 2 is the carbon behind, priority number 3 is the ethyl group, and priority number 4 is hydrogen. Okay. And now if I assign the stereochemistry, so if I have to look at it from this direction, then the hydrogen is actually remote to me, and then it actually is a anti-clockwise direction, and so I'm assigning this as S. So again, please go back and double check this and make sure that you're getting the answer correctly. And based on this, what I would predict is that the major product that is going to be formed is actually the S compound as shown here. Okay, so again I would when I convert this to the corresponding compound, you again want to double check that it's actually S. So this is 1, 2, 3, and so this is going to be anti-clockwise, and so therefore the assignment of the stereochemistry is S. So to answer the question, when this compound reacts with ethyl magnesium bromide, it actually forms a mixture of two compounds, and the major diastereomer, according to the Falcon model, is predicted to be S at this center.